Okay. Share screen. Share. Screen. Oh, I did a mistake. Okay. Stop sharing my screen.
دكتور بس إذا بجم تشي بيكي بالاستعمال كي برنامج أو أيقونة برغبة أن دو برغبة تيجا 3U Air Player
3U tools
3U Air Player نفيسيا أبرخ يا ريال تايم با أو بيكي بالجي شو لديك تشي ميرور كي والسر شاشة تدمين هندي أيبودات هلبت أو السر شاشة دمينت
اها
بيكي بالجي يعني كيبل إزعاجة أو أبديت جديد بي
بله نوكا اشتا من شير نكري هري هنا كشير سكرين ابايا نوكا باش انا
بلا سيد
درسته. Okay, now going back to the previous example, I'm in example number 2. We have talked about the two frequencies, 2000 and 3000 kilo. Again, please try to write down your names in the chat to be used for the attendance. Well, two frequencies, we have 2000 and 3000 hertz. We have sketched the spectrum for the X of F and the spectrum for S of F. This is S of F, sorry, S of F, and F is given in kilohertz. Now we are going to perform the convolution between these two signals, and then we are going to plot the sampled spectrum for the sample signal. Of course, in this time we have to be careful in drawing the signal or sketching the signal. Now this will be the F axis, frequency axis, F in kilohertz, of course, and this will be the origin of the signal. This will be X capital S of F, sampled function. Well, all we need to put ticks for the 8 kilo, okay, 0, 8 kilo and 16 kilo, minus 8 and minus 16. Starting with the first one, this performing the convolution between delta of F and X of F will be X of F itself. So we have the same copy of this figure at the beginning. 2, 3. Well, so this one will be the two frequency 2 kilo, and this one will be the 3 kilo. Okay, the convolution with the first one. Look please, this one is 2 and this one is a 3, minus 2 and minus 3. Now when we are going to perform the convolution with the 8 kilohertz, in this time what will happen? The center of the X of F will be transferred, okay, to the 8 kilohertz. So what we have, the frequencies, well,
11 and 10.
After, well, so at 10 and 11, Yes, at 10 and 11. On the other side, it will be at 8 minus 2.
6 and 5.
Yeah. Yes, it's good. 6 and 5. Okay, 6 and 5. So this one is 5 and this one is 6. And here we have 10 and this one will be 11. The same thing for the what? For the 16. Again, it will be 18 and 19. And here we have 14 and 13. Okay, 13, 14. This will be 18 and this will be 19. Okay, this will be the spectrum of the signal. Of course, the left hand side will be what? Will be the mirror for the right hand side. Again, what will happen to the signal, I mean recovered signal? Of course, we are going to use again a low pass filter with cutoff frequency equals to sampling rate divided by 2. So it will be 8 by 2, and this represents what? The cutoff frequency FC. So FC will be 4 kilohertz. So I'm going to plot, this will be the what? The 4 kilo, and this is the minus 4 kilo. Well, of course, using this one, what will be the remaining? The remaining will be the original signal, I mean 2 and 3, minus 2 minus 3. This will be the recovered signal, or XR of F and F axis. Okay, 2, 3, minus 2 and minus 3. In this example, we have talked about what? About a signal which is composed of more than one frequency. Here we have recognized two frequencies, 2 kilo and 3 kilo, and the sampling rate is fixed by 8 kilohertz. Now I'm going to go to a new example, which is example number 3. Okay, example number 3. It's a very important example, really. Well, example 3. Now we have another example, which is example number 3. Please look at example number 3. It's a very important example. Given an analog signal, okay, we are given the following analog signal, which is x of t equals to 5 cosine 2 pi 2000 t plus cosine 2 pi 5000 t. Again, the signal is sampled at 8,000 samples per second. Okay, requirements are: 1, sketch x of f and x s of f. The spectrum for the original signal and the sample signal. Number two, sketch the recovered signal. The recovered signal, if an ideal low pass filter with cutoff frequency FC equals to 4 kilohertz is used. Okay, in other words, it means what? We are going to plot X recovered of F spectrum. Okay, so this is the example number 3. Again, you can read the example number 3. We are given an analog signal which consists of 2 components, cosine 5 cosine 2 pi 2000 t plus cosine 2 pi 5000 t, and it's sampled at a rate of 8,000 samples per second. Sketch X of F and XS of F, I mean spectrum of the original signal and the spectrum of the sampled signal. Second requirement is what? Sketch the recovered signal if an ideal low-pass filter with cutoff frequency FC equals to 4 kilohertz is used. Okay, this is the requirement of this problem. Well, now we are going to solve this problem step by step, starting with the first branch, I mean X of F. Again, you can note the important point here. Look, 2 frequencies we have, 2 kilo and 5 kilo. Okay, so 2 frequencies we have, 2000, F1 equals to 2000, and F2 equals to what? 5000. Now, according to these 2 frequencies, F max will be 5000, and Nyquist rate Fs will be 2F maximum, and it will be 2 multiplied by 5000, and it will be 10,000 or 10 kilo samples per second. Okay, now look at this example. Now, in this example, this is the Nyquist rate. Nyquist rate is 10 kilohertz. We said that previously. To recover the original signal successfully, we have to what? We have to sample the given signal at least by sampling rate equal to Nyquist rate or greater. Look at this problem. We have restricted by what? Sampling rate equals to 8 kilo. Karanka. Yes, welcome. Any question? Do you have any questions?
No, sir.
It's okay. Well, now we have 2 frequencies, 2000 and 5000 hertz. Maximum frequency is 5 kilohertz, so the Nyquist rate will be 10 kilohertz. We said that for successful signal recovery, okay, we have to sample the input signal or X of t at least by sampling rate equals to what? Equals to Nyquist rate or greater. What we can recognize in this example? In this example, the Nyquist rate is greater than the actual sampling rate used in this example. So what we can expect?
We can recover the signal يعني as the before one.
What? Repeat it, please. Repeat what you have said.
We cannot recover the full
yes,
signal.
it's good. So due to this one, okay, so sampling rate in this problem, okay, sampling rate is less than Nyquist rate. From the beginning, we can note that the sampling rate is less than Nyquist rate. So such a signal, so the original signal can not be recovered. course, successfully. Well, so what will happen, of course, I expect that overlapping will take place. Okay, so in this case, we have what? We have overlapping. Well, so let us by now plot the spectrum for the original signal, spectrum for the S of f, and then spectrum for the sampled signal, and then we will be able to pass the whole spectrum through what? Through a low pass filter with cutoff frequency equals to 4 kilohertz, and then we will be able to determine the reconstructed signal, and is the reconstructed signal will be seems to be like that the original one or not. Okay, starting with the spectrum of the signal. Of course, going back to the same story. Well, here we have two frequency components, 2000. Of course, the 2000 frequency magnitude will be 2.5. Okay, this will be 2.5, 2 kilo minus 2 kilo. Their amplitude is 2.5. You know, by now you are familiar with the Euler identity, so you can use it easily. And this one will be the 5 kilohertz. Okay, 5 and minus 5, and the amplitude will be 0.5. The frequency, of course, in kilohertz. Look what's going on. Now we have two components, 2 kilo and 5 kilo. Their magnitudes are 2.5 and 0.5. Well, the spectrum for the sampling function S of f will be at 0, 8 kilo, and 16. Minus 8 and minus 16. Okay, this will be the spectrum for the signal, and this will be f in kilohertz. Now let me show you the whole spectrum of the signal. We have to be careful in sketching this spectrum in this time, okay, and try to avoid errors. Well, 1, 2, 3, 4. This take for 8 kilo. Okay, this will be, say, 8 kilo. 0, 8, and this will be the 16. 1, 2, 3, 4. Minus 8, and this will be the minus 16. I'm going to use different colors to illustrate what's going on. Now, first frequency component will lie where? At 2 kilohertz. Well, this is at 2 kilohertz with amplitude equals to 2.5. So this will be at 2, and this will be at minus 2. The other frequency component will be at 5, and its amplitude equals to 0.5. Okay, this is 0.5, and this one is 2.5. This is what for the first one. Now, what will happen when we are going to perform the minus 5? Well, to perform the convolution with 8, what will happen? Look, please. First component will be 8 plus 5, and it will be what? It will be 13. Okay. The other one will be 8 plus 2, and it will be 10. So we have two components. Please look at. We have two components. First one will be at 10. Okay, this is at 10, which is 2.5. The other one will be at 13. 10, 12, 13. This is the 13, and it will be 0.5. Well, 10 and 13. What about the other values? Look, please. We have 8 minus 5. It will be 3. And 8 minus 2. It will be 6. So we have another component, which is 8 minus 2. Okay, 8 minus 2 and 8 minus 5, sorry, yes, 5 and 2. Okay, 8 minus 5 will be what? Will be 3. Okay, so we have a component at this point, I mean at point equal to 3. This is 2, 3, 4, this is 3. At this point, we have another component, 3. Other one will be at 6. At 6, this one will be at 6 and equals to 2.5. Okay, this is due to what? Due to the convolution with what? With 8 kilo sample. Let's go to the what? To the other side and perform the convolution with -8. With -8, in this time with -8, -8 minus 2 will be what? Will be -10. Okay, -8 minus 5 will be -13. Of course, this will be the mirror for the previous case. Okay, so here at this point we have 10, and then we have at -13. Okay, -13 and -10. We don't have any problem with these points. Okay, now what will be about the other points? Here we have -8 plus 2 and -8 plus 5. Okay, -8 plus 2 will lead to -6, and -8 plus 5 will lead to -3. So again, we have components at -3. This will be at -3. Well, -3, and we have another component at -6. Okay, this is for the what? For the second convolution, I mean with -8. Of course, we may what? We may perform the convolution with 16 and -16. Again, it will be a very simple job. With the 16, again, it will be very simple. Let us try it. Now with 16, it will be 16 plus 2 and 16 plus 5. Of course, it will be 18 and 21. So at 18, we have a component, and at 21, okay, this is another component. What about the other values? We have 16 minus 2 and 16 minus 5. 16 minus 5 will be 11. Okay, so at this point we have another one, which is at 11, and 16 minus 2 at 14. We have another component. Well, at this point exactly, this is the point of 14. Okay, now this is the spectrum for what? For X S of F. So you have to be careful when you are going to solve such a problem. Now, what about the other requirements of this problem? We are talking about a low pass filter with cutoff frequency equals to 4 kilohertz to be used for what? To recover the original signal. Now, do you have any questions, please, up to this point?
Yes, here.
Yeah.
When we said 16 plus 2 equal 18, the amplitude will be 0.5 or 2.5?
Yes. Look, please, go to the starting of the example. Look, Here we have 5 and 1. Okay, cosine means 1. If you are going to apply the Euler identity, so 5 divided by 2 will be 2.5. I mean, the magnitude for the 2000 will be 2.5, and the magnitude for the 1 kilo, for the 5 kilo is 1. 1 divided by 2 will be 0.5. Okay, this is about the magnitudes used in the spectrum. Yeah. Any other questions? Do you have other questions? So let me show you something very simple, okay, to remember, always remember. Look at this is the what? This is the original signal. Please look. This is the original signal. We said that we have two components, one of them at 2 kilohertz, 2 minus 2, and the other at 5 kilohertz, okay? We said that another one is at 5 kilohertz. Now, how we are going to perform the shifting process? Please, how we are going to perform the shifting process? Now, this is 0. When we talk about, say, for example, convolution with delta of f minus 8, what does it mean? It means that the center of this figure becomes what? Becomes 8. Okay, 8. So what does it mean? It means 0 plus 8, then 2 plus 8, 5 plus 8, okay? Minus 2 plus 8, minus 5 plus what? 8. So the whole point of the figure will be what? Will be shifted by plus 8. That's it, no more, no less. So it becomes at 8, okay? 2 plus 8, 10, and 13. On the other hand, we have what? We have minus 2 plus 8. So it will what? It will performs a component at 6, okay? The other will performs a component at 3, as we have seen before. The same thing for the what? When we have, for example, minus 8, at that time, every point in this graph will be shifted by minus 8. That's it, no more, no less. This is about what? About performing the shifting process for the original signal. So at the beginning, the figure will appear at the origin, I mean 0, then the center becomes at 8, then the center becomes at 16, and so on. Now, let us go to the third requirement. Here we are talking about what? About the recovering the original signal. I mean x recovered of f. Of course, how we are going to determine xr of f? In this time, you have to be accurate when you are going to draw the borders of the filter. Look, here we have 3 and 5 in between. Here we have what? 4. Okay, this is the point of 4, and this one the point of 4. Well, this is the borders of the low pass filter. Okay, any component inside the box will be multiplied by what? By 1. Outside the box, the whole components will be multiplied by 0. So in this way, we are going to make filtering or performing the filtering between what? Between minus 4 and 4. Look, going back now to the XR of f. Now we are going to plot XR of f. XR of f, and f in what? In kilohertz. Now, what will be the output at 2? Well, 2.5. Sorry, let me clarify the now at 2 we have 2.5, and at 3 we have 0.5. This is 0.5, and this is 2.5, and f in kilohertz. Of course, this represents what? Represents the recovered signal. 2 and 3, minus 2 and minus 3. Of course, if you are going to use the inverse of the Euler identity, I mean, or we are going to describe these components easily. Look, it will be 2.5, sorry, it will be 2.5, yes, 2.5 or 5 over 2. Let me write it as in this form to be easier. 5 over 2 e to the j 2 pi 2000 t plus e to the minus j 2 pi 2000 t plus 1 over 2 e to the j 2 pi 3000 t plus e to the minus j 2 pi 3000 t. Wow. So xr of t, look please, xr of t will be 5 cosine 2 pi 2000 t plus 1 cosine 2 pi 3000 t. Have you seen? Now x recovered has two components, 2000 and 3000. Look at the original one. Original one was what? Was 2000 and what? And 5000. What will happen? What's going on?
Clipped.
Yeah. What you can recognize?
Signal is not recovered fully.
Yes, signal is not recovered. But what is going on? We have what? We have fed the system. Look, please. We have fed the system by what? Let me show you, illustrate it clearly. Okay. Now, input, please look. Input was what? F1 equals to 2 kilo and F2 equals to what? 5 kilo. Of course, hertz. Now, output, the output of the system, output F1 is equal to 2 kilohertz still, and F2 equals to 3 kilo. Well, so input to the system is 2 kilo, 5 kilo, and output is F1 equal to 2 kilo and F2 equal to 3 kilo. So what's going on? Of course, the output or the recovered signal is what? Is different from what? The original signal. Due to what? Due to?
Sampling.
Due to improper sampling rate. Now, can anyone tell me the required value for the sampling rate to be what? And for example, in this example, we have considered 8 kilo sampling rate. What will be the true value or the correct value to be able to recover the signal?
10 kilo.
10 kilo and over.
The second one, 10 kilo and over. Okay. The correct answer is what? 10 and above. Okay. Or over. Well, it's good. So at least we have to what? We have to select the sampling rate equals to 10 kilohertz. Of course, 10 kilohertz is not preferable. Why? It requires a very accurate, very sharp edge of a low pass filter. But if you are going to consider, for example, sampling rate equal to 12 kilohertz, 13, 14, 15, 20 kilohertz, all of these are what are better than the 10 kilohertz. Okay, so we have to what? We have to use at least sampling rate equals to 10 kilohertz or greater. Okay, This is about how we are going to select the correct value for the sampling rate. Now, I have another question or example for you, really, to end up the lecture. Okay, now here we have, say, a simple example. Sorry, yes, example. Now, given a signal x of t equals to e to the minus 3t, okay, of course, for t greater than 0. Well, for t greater than 0. The requirement is convert this signal into discrete time signal using sampling rate of 1 kilo kilohertz or 1 kilo samples per second. What we are going to do to solve such a problem? Okay, now this is the last example in this lecture. You are given a signal called x of t equals to e to the minus 3t for t greater than 0, and the signal is sampled at a rate of 1 kilohertz. The requirement is what? To convert this signal into discrete time signal. I mean x of n. Well, so the requirement is x of n. Of course, you have to keep in your mind this formula. X of n equals to x of t when each t is replaced by nts. Okay, when each t is replaced by nts. Now, how we are going to pick up ts? Ts is equal to what? 1 over fs. Fs is given by 1 kilo, so Ts will be 1 over 1000. Okay, so Ts will be 1 millisecond. Okay, continuation. So x of n will be what? E to the minus 3 multiplied by 10 to minus 3n. Okay, so x of n will be e to the minus 3. Now, instead of each t, we are going to put what? To put nts, okay? N, and the value of ts is 1 over 1000. So it will be e to the minus 3 multiplied by 10 to minus 3n. So in this way, we can what? We can calculate x of 0, x of 1, x of 2, x of 3, and so on. Now, as a homework, okay, you can use a simple MATLAB program to plot x of n with these information, okay? Plot the signal using the MATLAB program for this will be the n-axis, and this will be the x of n. Take n-axis up to 100, okay, from 0 up to 100. Do you have any questions, please? Any questions? Is everything clear?
Yes.
You have to say something. Huh? It's okay. Thank you very much. So, inshallah, next week we are going to talk about the aliasing. Of course, aliasing needs some derivation, and we are going to talk about the aliasing with the derivation and some numerical examples, inshallah. See you in the next week. Goodbye.
Teacher, sorry, but just about MATLAB, we do it for ourselves, or we send it to you?
Yeah, do it by yourself. Yes, MATLAB.
Yes, we will do it by ourselves. Yes, but is it our homework? We send it to you, or just for ourselves we do it?
No, as a homework, This will be a homework, okay?
So we send it to you. After we imply it, we send it to you.
Yes, through, for example, on the model, I will give you a chance to upload your examples or the homework, okay, to the model.
Okay, teacher.
Yeah, it's a very simple program, okay? So you may upload by just M file, a small M file, you may upload it to the model. Well, I will give you
Okay.
to the end of this week, the time, okay? The time will be given for you up to the end of this week. Well?
Okay, teacher.
Okay. Anything else?
No, all things is clear.
Okay. Thank you very much.
Thank you.
Goodbye.